If you are drawing a process and instrumentation diagram from scratch, start with a grid coordinate system. All p&ids that I've ever worked with have this, even though I don't think I've ever used it. There's always letters on the one side, numbers on the other, so that you can refer to grid coordinates if you ever want to, I don't know, refer to the location of a specific instrument on this drawing. Next comes the title block. It's got the company name and it's got the company logo. It could be the operator of the plant, it could be the engineering company doing the p&id, it could be both. Next, you need the name of the drawing, so what is it that we're showing on this drawing, as well as a revision history. The revision history contains small details about what's changed in various revisions of this drawing. So you'll find things like first issue, issued for design, approved for construction, as built, meaning, okay, we've designed the thing and built it, but is the thing that we installed even reflective of what's on the plant itself? If not, we should update the drawing. You obviously need a drawing number, like a document number, which we should have started with because the revision history refers to this specific drawing number. And drawing numbers also have different sheets, so I could have multiple sheets for the same drawing number. This one is going to be called sheet 2 because that's what I feel like. And in the corner is usually the revision number that you're dealing with so that you can quickly check what revision you're looking at without going into the revision history block. There's all sorts of other things that appear here, such as the date, who drew it, who checked and approved it, what unit number is it, where's the location of this site, all sorts of other things. We're not going to go into all that detail here. Right, so what is it that we're going to draw on our p&id? Well, it's going to be a tank. There's standard symbols for tanks depending on specific design elements. One can use these, but it's also quite common to try and reflect what the tank looks like in real life and try to get it in proportion with how it's actually built. All equipment needs a tag number. We're going to call our tank T101, T for tank. But here I'm writing a couple of options in red. Maybe on your site you refer to tanks as TK, or tanks have the equipment number starting with V for vessel. Maybe you use the letter A to designate tanks. That you can only know from the site you're working on. Another common thing that happens, which I haven't shown here, is that the tag number is preceded by the unit number, especially if this is one plant on a bigger site. Apart from tanks, pumps, heat exchangers, distillation columns, reactors having tag names, all instrumentation, valves, transmitters, and so forth will have similar tags. The way equipment will be named and numbered and tagged is usually agreed upon by the customer, the plant that's going to own and operate this plant, and the engineering company who develops the drawings. And that's done right up front before the project even starts. Along the top of the p&id, we usually write all the main pieces of equipment so that it is easy to locate it on the drawing. The header will contain the tag number, the name of the piece of equipment, relevant information. So for example, a heat exchanger might have a duty, a pump may have a power consumption and a capacity and a head. For our tank, the relevant piece of information is the volume. We're also going to put the design pressure and the design temperature. Let's just make it up and say the tank is designed for a maximum of 80 degrees and it isn't a pressure containing tank, so we write hydrostatic to say that the only pressure it's designed to handle is the pressure exerted by the liquid inside the tank itself. Now what's flowing into the tank? It's coming from somewhere, so we indicate this with an arrow, and next to this arrow we write what is it that's flowing, where is it coming from, so usually we write an equipment number. This one we've said is coming from R101, meaning reactor 101, but it's most likely usually pumped from another pump, so you'd write the pump name. And you also write the sheet number and the drawing number that connects this sheet to another sheet, meaning it's the same line that crosses across these two different sheets. Now that we have a line running into our tank, that line needs a number. The label that we put on the p&id is going to contain a lot of information. The order of these different pieces of information will be specific once again to the site. So what I'm showing you here, I've completely made up. The first letter is what we call a pipe fluid code. So at a quick glance, you can get an idea what it is that's flowing in the pipe, because you usually wouldn't be able to tell from a p&id because all the lines look the same. They're just black lines running all over the place. But if I look at this one specifically and it has the letter A, I can think, oh, I know that A is the fluid code for my product. Other fluid codes could be something like steam, cooling water, nitrogen, refrigerant, instrument air. So all of that will be specific to the site you're working on. The next number, I've got 10,001, will be the actual line number. That refers to the pipeline. No other pipeline will have the number 10,001 on my plant. Next, I put the nominal size of the pipe or duct that I'm dealing with. This one is an 8-inch line for argument's sake. Then we give it something called a piping class. Don't confuse this with the fluid code. The fluid code tells us what is inside the pipeline. The pipe class tells us what the pipe is made of. So the pipe class isn't exactly a material, it's a collection of materials. So as an example, I could have my product flowing in a plain carbon steel pipe, which let's pretend this one is, and we've called that pipe class C1. But maybe in other areas I have stainless steel, or I have stainless steel that's also coated internally with a special liner. The pipe class is a very specific description of what materials are used. So it's useful because you can say something like, oh, you're transporting steam. Usually we use pipe class X, but we can also use pipe class Y to convey steam as long as the temperature of the steam doesn't exceed so many degrees. Apart from the pipeline material itself, the pipe class also describes which valves and flanges and nuts and bolts I'm allowed to use. It's quite a detailed thing to go into, so don't worry about it too much. And if you're submitting a p&id for, say, a university assignment, you can't really be expected to even know this. So this is just for information. Finally, the last letter is usually the insulation code. So if my line isn't insulated, I could put something like N to say no insulation. If I do insulate it, I usually say why I'm insulating it. So H means hot, C means cold. That means that I'm trying to keep the fluid inside the pipeline hot or cold. I could also be insulating the pipeline not to conserve heat or keep something cool, but rather because I'm more concerned for the safety of the people on the plant. I don't want them to touch it by mistake and get an injury. Similarly, I could have acoustic insulation to dampen the sound of the flow inside the pipe with no regard for the temperature of the fluid inside. I can also steam trace or electrically trace pipelines in order to keep them hot. Another thing I forgot to do, which is quite common, is to put a little 2x2 block onto the line to show firstly the operating temperature and pressure, and then the design temperature and pressure. The operating temperature and pressure is what you expect as a maximum on your PFD. So when you're sizing your equipment, you've picked, even though it's the maximum, that's not to say the design. When we talk about design, just like I did at the top of the sheet, there we're referring to the mechanical design, meaning the temperature and pressure that this piece of equipment or this pipeline is constructed to withstand. And that's usually higher than the maximum operating, obviously. Right, so now this pipeline somehow needs to connect to my tank to be able to deliver the product into the tank without spilling it all over the place. We do this using flanges. The flange is the face that runs around a pipe that receives the bolts that can mate with another flange in order to connect two pieces of piping or a piece of piping to a tank. The flange on the tank side and the whole jutty outy bit from the tank, That assembly is called a nozzle. A nozzle can be on a vessel in order to attach pipes to it, but it can also be there to attach instrumentation such as pressure, level, and temperature sensors. Nozzle sizes differ according to the size of whatever it is you're trying to attach to your vessel. The reason I mention this is that while I don't need to show every flange on every single pipeline, nor do I need to show things like bends for that matter, I usually do show the flange that attaches a pipeline to a nozzle on a tank. I also give every single nozzle on a tank or reactor or column or vessel a number. And that's because later on, when the drawings for this tank, heat exchanger, whatever is being done, I will carry on using those same nozzle numbers so that I can link nozzle numbers on my p&id to nozzle numbers on detailed equipment drawings. The nozzle numbers have a specific format, also site dependent. What I've done over here is I'm saying that all inlets to my tank will be preceded by the letter A. Next, we're going to put a valve on the line into our tank. This is to be able to isolate the line, say, if we're maintaining the tank. Now, discussing the symbols used in p&ids is obviously important, but it is a very slippery slope and I don't want to go down that rabbit hole. Something as basic as a gate valve. You'll see the symbol on the left in blue as the most common symbol, but there are other options given by various standards. So while it may be confusing at first, know that most of the stuff is set out right at the beginning of a project, and actually most process and instrumentation diagrams come with a cover sheet that say, here are the symbols that we agreed to use that represent these pieces of equipment. Although it isn't always done, I've seen many p&ids where the size of the valve is written next to the symbol of the valve. So here I'm writing that it is an 8-inch valve, which is the same as the line size. It is possible that we have a reducer on the line, and a reducer means a reduction in the pipe diameter. This is a symbol for I'm drawing it in red as an option, a concentric reducer, and we write above it that the line size is going down from 8-inch to 6-inch, which also means that the valve we use needs to be smaller, so this would be a 6-inch valve instead. And all of this would translate into the nozzle on the tank also being the same size. So if I've used the reducer, nozzle A1 on the tank is a 6-inch. If I haven't, it's simply 8-inch. Here you can see that I've forgotten to show that the line is insulated. I don't need to draw the symbol across the entire line, just a portion of it to indicate that the entire line is insulated. Now we need an outlet, right? The product in this tank is going to go somewhere, so the outlet nozzle is what I'm drawing here. And just like I said, my inlets will be designated A, my outlets will be designated B. That's just one way of doing it. A lot of standards simply label all regular process nozzles, in other words, with regular fluid flow coming in and out of them, as N. So maybe I could have called these N1 and N2 and lost the ability to differentiate whether it's an inlet or outlet. Just like I had a valve on the inlet line, I should have a valve on the outlet line too, for the same reasons. I want to be able to isolate the tank. And here is my line that comes out of my tank and goes to another sheet. I'm writing that this line is going to a pump because I'm going to be pumping out of this tank, and I put the pump number as well as the sheet number. This new line needs a number, so I'm going to write that here. The piping is the same as what I used on my inlet, but the only thing that changes is I need a new number, so I call it 10,002. I show that the line is insulated, just like I did with the inlet line, and for good measure we draw a little bit of insulation on the tank too, to show that we've insulated the tank to conserve heat. Now let's say we need a way of measuring the temperature of the liquid that's going to sit in this tank. We need, just like earlier, a nozzle to attach our temperature measurement to. We call this nozzle T1 to indicate temperature measurement. By far the most common way of measuring temperature on process plants is through using something called a thermocouple. A thermocouple is two wires made of dissimilar metals connected together. Now, you can't reasonably expect something like this to withstand the conditions inside a tank or a pipe. So the thermocouple itself needs to be protected by something called a thermowell, which is usually a steel casing within which the thermocouple resides. On a p&id, we show both these elements. The thermocouple itself is labeled TE, as in temperature element 101, and of the same nozzle we put a symbol for the thermowell and label it TW 101. The signal comes from the temperature element, not the well. The well is just the steel casing. And that signal is transmitted with a dotted line as opposed to a solid line to a temperature indicator. And talking about this made me realize that I've actually made a mistake, and that if I wanted to be absolutely correct, I should have a temperature transmitter that takes the element reading and sends it to the indication on the control panel. So what I'm showing over here is how I would accurately show a thermowell, the thermocouple sitting inside the well, the transmitter that takes that reading from the thermocouple and attaches to cabling that runs to the control panel, and it's finally the indication on the control panel that I see. Now, I've worked with many different process and instrumentation diagrams, and I can assure you that not all of them go into this level of accuracy. In fact, it is very common to simplify this arrangement to something like this. Whether it's correct or not is another matter, and while it does not show every single piece of instrumentation that make up this loop, it does communicate the idea of what we're trying to do. I'm not advocating for doing one over the other. I'm simply showing you this so that you're aware that you may encounter things like this. My advice to you, especially if you're new to process and instrumentation diagrams, is do not aim for perfection. If you do, you are likely to fail. You can see that I also forgot that I should have indicated the transmitter on the drawing. Let's also pretend that we want to know if our fluid inside our tank gets too hot. So what we would do is put an alarm on this temperature indicator, and we can indicate that in two ways. One way is to put AH as an alarm high next to the symbol for an indicator, or the other option is to draw another block that says TAH, temperature alarm high, as a separate block next to the temperature indicator. Now, you wouldn't do both. You'd either use the separate block or you'd put AH. I have seen both once again. Now, apart from temperature, we obviously want a level measurement. We want to know how much fluid is sitting in our tank at any given point in time. A common way of measuring level is through using a differential pressure transmitter. So this would be the same instrument that would be sitting across, say, an orifice plate on a flow meter, but we use the fact that it can measure a differential pressure to connect to a tank and tell us how much liquid is in that tank. And it's able to do this because the liquid is exerting a pressure onto this transmitter. More liquid in the tank, higher pressure exerted on the transmitter, meaning we'll register a higher pressure and then we translate that pressure into a percentage level. The differential pressure transmitter, or DP cell for short, requires two connection points. So we need two nozzles, one at the top of the tank and one at the base of the tank. Those are going to be labeled L1 and L2 respectively, L for level. We hook up both legs of our DP cell to these nozzles and we show the DP cell as LT101, in other words, level transmitter. It doesn't matter that the instrument we're using is primarily used to measure pressure or differential pressure. Because the application is in measuring level, it's labeled L. If it was used across a flow meter, it would be labeled F. Now, the picture I showed you of the level transmitter on the left, you can see that it actually has a digital display, meaning I could locally see what the reading was. If this was the instrument used, I would have used the label LIT, level indicator transmitter, because there is an indication. However, many DP cells don't have that indication and are simply a transmitter. In that case, we use LT without the indication. Now don't get confused, I can still see the reading from a level transmitter. It's just that the indication takes place on the control panel that's taken the transmitter and interpreted the value. Let's say we want to control the level in this tank. What we would do is take the signal from the level transmitter and send it to a controller, a LIC, level indicator controller. So in this instance, the level is a controlled variable, that's why there's an LIC, while the temperature is simply for indication, and that's why we have no TIC. It's not that you couldn't do it, it's just that we're not doing it in this case. For our level controller, we're going to take the signal from that controller and we're going to send it to a valve actuator. An actuator is just something that makes the valve move up and down. I'm calling that actuator LY101 and I'm showing that it is on another sheet because we haven't drawn the valve on this pipeline. Now a valve is one way to control the level, but we could also use the speed of the pump pumping out of this tank to control the level. So if we were changing the speed of that pump, we'd say it's going to SC101 or speed controller 101. Now I'm going to show you what we would do if we had multiple instruments. Let's say controlling the level in this tank is process safety critical, and we didn't want to rely on just one instrument, we want multiple instruments to do the level measurement. We would install 3 level transmitters, and the numbering would be A, B, and C, but all of them would be labeled LT101. I keep the number the same and use letters at the end to denote that I'm using different instruments to measure the same variable. If it was LT102, it would imply that I'm measuring a different level to LT101. So I keep the number the same but add letters if I'm using multiple instruments to measure the same thing, say for safety's sake, because I want to be sure the reading. If I change the number of the instrument, it means that other instrument has a different intention and likely I'm expecting a different value. And apart from instruments, this also applies to numbering equipment. If I have a pump, for example, called P101, if I have an A and a B pump, it implies that they're both there to achieve the same thing. It's just that the B pump might be the standby pump in case I'm maintaining the A pump. But P101 and P102 implies they have different process functions. The 3 separate signals from these 3 different DP cells are sent to a calculation block, and the function of this block is to select the middlemost value. So it is common to see either MO3, in other words middle of 3, or the word median next to blocks like this. Middle selectors are usually designated with Y, so because I'm selecting the middle level, I call it LY. If I was selecting between 3 temperature transmitters, I'd call it TY. Now I called it LY101, which I can't do because I already have an LY101, and that's the actuator I'm sending the signal to. So that's why I'm correcting that and renaming it 102 instead. It's only the middle value that's sent to the controller because the controller can only take one input to check what the process value is. If the transmitter that's recording the middle value happens to fail, then transmitters are usually designed to fail either high or low, meaning it will go to a very high value or a very low value, and that means one of the other transmitters becomes the new middle value, so your control stays stable, assuming your values were similar to each other to begin with. Next to the LIC block, the controller, I'm going to write AH and AHH. AH is the alarm. It means alarm high. It indicates that the level is high and it will sound an alarm for the operator for them to be able to take action to try and remedy whatever is causing the high level. If the operator fails to take the necessary action to stop the level rising and the level goes even higher to the high value designated by AHH, then I have something called an interlock. An interlock is where I have connected the operation of another piece of equipment to this instrument, and it is a safety feature that will prevent me from overflowing this tank. The interlock will cause something else to happen. So I could, for example, trip my entire plant, or I could trip simply just a piece of equipment upstream of it to prevent any more liquid building up. So I've written AHH, but sometimes p&ids won't show that AHH. Instead, they'll show a completely separate block to show the high-level trip, like I'm about to show you now in red as an option. I draw a dotted line from the level indicator controller to another block, which I label LAHH, level alarm high high 101, and I show that instead of a dotted line, now I have a digital line denoted by what looks like the string of beads to a diamond with I4 in it. The 4 I've made up. The I stands for interlock. You will also find labels such as ESD in blocks like this instead, which means emergency shutdown. The 4 designates that very specific actions decided up front will happen if interlock 4 is activated. We create dedicated drawings called cause and effect diagrams that would describe everything that would activate interlock 4, so those are causes, as well as what interlock 4 does. Those are effects. So we've got a whole bunch of actions for a high level. For a low level, we'll take a different set of actions. So you can see I've already written alarm low, AL, as well as alarm low, low next to the LIC. Now I'm adding another block that says what the interlock, the low level interlock does. That I'm calling level alarm low, low 101. And that is going to another interlock diamond, which this time I'm calling 5. And interlock 5, the effects of interlock 5 will be different to the effects of interlock 4 because I want different things to happen when the level is low as opposed to when it's high. What we call high and low depend on the specific design of the plant and the considerations around why we would want to stop the plant or trip something. But one thing I forgot to do is to show that often on p&ids, we show what these levels actually are in height terms. So we put them in millimeters or inches. And what you see here is the middlemost value is the normal liquid level, NLL. And that would be where we want to, that our controller would be controlling. Then you have a low liquid level, that would be my alarm, and a low liquid level, which is sounding ridiculous, but that would be my low trip. Similarly, I have a high level and a high level, which represent my alarm and interlock values respectively. Now I would have this for tanks, but I would also have it for any other piece of equipment where I am expecting to build up a liquid level. So it could be a knockout drum, a distillation column, a sump, a scrubber bottom, any of those sorts of things. Right, to finish this up, we're going to add a few practical things to our tank. The first thing will be to add a drain to be able to drain the contents of this tank. So we put a 2-inch gate valve and we attach it to nozzle D1, D for drain. And it's common to write a little note to show where it is that we're draining this tank. So something like to sump, to drain, or to sewer. Next, we add a vent to our tank and we put another valve on that. And just like with the drain, we write a note. Vents typically say things like to safe location. And if you think about it, these p&ids are generated before the plant is built. So the purpose of this note is to show the people who are eventually going to be designing that vent line and doing perhaps a 3D model review of the plant. They need to then check, is this vent actually going to a safe location, or is it going to blow into someone's face climbing up a step ladder? So that's why we make these kinds of notes on p&ids. Next, we add a manhole so that we've got some way of accessing the tank internally in case we need to clean or inspect. And manholes are denoted either M or MH. So I've written M1 here, and 24 inch is a good size for a manhole. That's about ½ a meter. And there you have it, a p&id for a tank and 2 lines. You can see that even though there's not much equipment on this, it's quite easy to fill up a p&id, and that's why you shouldn't feel the need to force too many pieces of equipment onto one p&id. Undoubtedly, There are things here that are likely incorrect or inaccurate or should have been done differently. You are going to see many different things in your career. So hopefully this has given you a bit of an introduction. And if you're using this to do a p&id at university level, well, understand that there's a lot of detail here that you just can't be expected to know, but hopefully it sets you on your way.